So good afternoon, everybody. So my name is Estelle. I'm a PhD candidate in geography working at LISER and enrolled at the University of Luxembourg. The current research I'm going to present to you is in collaboration with my thesis supervisor, Professor Geoffrey Caruso, and also with Dr. Rémi Lemoy, researcher at the University of Rouen in France. Today I'm going to talk about our analysis of travel times inside European cities. In general, in my thesis, I'm working on introducing a new perspective of urban form through the radial modeling of road network patterns in Europe. So the travel times and the travel distances, basically. First of all, I'll give you some information about the context. So why am I researching this topic? It's important to note that the present study is part of a larger endeavor to formally and empirically establish the relationship between urban form and city size. So personally, I am focusing on intra-urban road network characteristics, while other people in the team are studying other aspects of urban form, for example, the profile of built land, the profile of green land cover, the pollution, and so on. So the study contributes to building a complete characterization of European cities by assembling all their facets in the same fashion, which is in a radial perspective. So the general philosophy behind this research and behind most of the urban scaling literature in general is to understand which kinds of urban forms and which size of cities are resulting in which kind of transport-related outputs. So is it more efficient in terms of the travel characteristics and the related impacts, like pollution exposure, for example, to distribute the population in several small urban areas, or whether to concentrate it in a very few, very large cities? So this is the question of agglomeration effect, the economies or diseconomies of scale. More specifically, the research is aimed at understanding how Euclidean distances and road network distances and times change with population space and vary across the European continent. So I'm doing a systematic quantification of travel times in Europe over a wide range of city sizes. And this quantification is relevant to indicate the over or the under expansion of cities given their size. And also so far published comparative studies on urban sprawl in Europe are highly dependent on the indicators used to characterize urban forms. And here it's a standardized method to study cities. Some other motivations for this paper are that in the literature of urban form, there is no measure considering both at the same time urban road networks and the spatial distribution of the population. So the types of moves are influenced by the land use and the road network shape, which are rarely considered together. And finally, most morphological indicators are based on Euclidean metrics, and they ignore actually the transport infrastructure, while we know that travel times are really important to assess transport costs. For example, straight line distances are often used in urban modeling or in urban economic models, where transport costs are assumed to be directly proportional and equal to the as the crow flies distance. It's the hypothesis of a continuous space without any friction or geographical constraints. But yeah, however, Euclidean distance is a very poor accessibility estimator. So a distance measurement between pairs of locations more representative of the reality would considerably increase the quality of these models. All right. So here we are doing an empirical investigation of how the internal radial structure of the European city scales with its population. And we combine in the research the study of the internal structure of cities and the study of systems of cities. So we go we move from the intra-urban scale to the inter-urban scale, and conversely. So the first point is to identify an empirical relation between straight line distances and travel times on the road network in the form of radial profiles. And the second point is to understand how this relation varies with city population and across space. Yeah, because cities are expected to share the same simple average dynamics underlying their road network characteristics over a wide range of spatial scales. So the presentation of today will focus on the second point only, not on the profiles, but I'm still mentioning that because it's an integral part of the research logic. Here, the analysis of urban form is described in accordance with the urban economics model of Alonso Mills, the monocentric city. So we are examining the radial profiles in relation to the road network characteristics, so which is the theoretical simulated automobile travel distances and times on the network. So we measure empirically the time distance between all populated areas, actual residential land use locations, and the CBD as the main attractor of trips. We estimated the CBD by the location of the city halls, and we take the fastest path in terms of time on the road network using the Google Maps algorithm. I will come back to this in a minute. So this is quite a strong assumption, but it is methodologically useful because it allows first an effective simplification of cities. Second, it allows to engage the dialogue with urban economic actors that consider space in one dimension. So it's obviously not a substitute, but a complement to simulations in two dimensions and in heterogeneous space. This assumption is also useful to reflect upon policy instruments that are directly based on the center-periphery distinction, such as, for example, green belts, urban tolls, housing policies, and so on. Okay, so the time metrics, so the travel times were computed on 303 cities. I took the land use maps of the Urban Atlas of 2006. The cities are usually more than 100,000 inhabitants. And the border of these functional urban areas is defined by the limits of the city center's employment attraction zone. So it makes sense in this case. So this is the first data source, and the second data source is the population grid at the 1 square kilometer spatial resolution by Eurostat. And then we combine the two data sets. So this is just an example for one city in Belgium. So this is how it looks like. And by means of GIS techniques, a systematic unaligned sampling of the exact residential land use locations was performed to limit the time and the monetary costs of the massive routing calculations. So I took one random residential point per 1 square kilometer grid of Eurostat. So these are the light gray squares. So this allows to represent the original density distribution, so a few high density residential plots in the center and many low density cells in the outskirts. So the calculations can be seen as an accessibility assessment of the city centers by the inhabitants in a center-periphery analysis. And Google also records the path taken by the inhabitants. So it records the coordinates at each change of direction. So to derive this measure of congestion in cities, we use the Google Service Directions API, where we enter itineraries between every sampled residential point and the city centers. And we compute these trips at optimum traffic conditions and also in live traffic conditions once per hour for the 24 hours of the day. We chose a typical weekday, a Tuesday of September. So this results in more than 7 million trips at the end for the 300 cities. So this is to exemplify you how the results looks like. So this is only for one origin destination trip in Brussels. In blue you have the trip to the center, and in orange you have the trip back to the periphery. So we decided to compute the outward trip in the morning and the return trip between noon and 3 a.m. In the morning. So you see that the peak is very localized. This is another formatting of the data we get from Google. It's in the form of radial profiles, so going from the CBD to the suburbs. So the graph on the top left is the travel times at night, assuming there is no congestion. And the one on the bottom right is the travel times at the morning rush hour with live congestion. The curves are only a sample of representative city sizes of the data sets. We already see in these radial profiles that the time cost is actually not linear, contrary to the transportation cost hypothesis in urban economics and economic geography. This is not the focus of the presentation, but we see that people spend more time traveling per unit of straight distance close to the center than far away from the center. The road transport time is concave. Speed is increasing with the distance to the city center. So this is already quite striking, and it represents already a global travel time profile for Europe. Yeah, we need more analysis to see whether population involves this economy of scale in terms of time spent traveling on the road network from this graph. So in this presentation, I will focus on aggregated measures of travel times. We do this analysis in 3 main steps. So first of all, we identify the congestion peaks. So one in the morning, one in the evening, and also one night low, which is the fastest travel time among all possible departure times for each city. So one departure time out of the 24 hours of the day. Secondly, we compute some congestion indexes for the peak departure times in absolute and relative terms. And we also weight these indexes by the population at each origin on the entire urban area. And the third step is to compute these indexes on rescaled cities and to add a public transport counterparts. So how do we to identify congestion peaks? So we localize the departure time with the maximum trip duration for each row, so for each origin destination trip. And then we count how many maximum trip duration there are for each departure time. So we select one highest frequency of maximum trip duration in the morning and one in the evening. The most frequent morning peak is at 8 a.m. and the most frequent evening peak is at 5 p.m. In the whole data set of cities. And the night low, so the time where there is the less traffic, is at 4 a.m. in most of the cases. So yeah, there on the map you can just maybe see that the morning peak is slightly later in southern European countries, but yeah, this was more an intermediate step to compute the aggregate congestion indexes afterwards. Okay, so after that, we have congestion indexes in absolute terms, which is just simply the average or the sum of the difference between the trip duration in the morning compared to the trip duration at night. So this goes up to 45 minutes on average on all trips for very large cities. And the average excess travel time is 8 minutes. So this is quite a substantial time loss. We also have relative time losses, so the trip lengthening in percentage when we divide the time difference by the travel time at night. And the third column is the time loss per traveled distance, so per kilometer. We have a mean on all cities of 28 seconds per kilometer of time loss when traveling in the morning peak compared to traveling at night, for example. So this is the spatial heterogeneity in the excess travel time in seconds lost per kilometer. This allows us to identify some explanatory variables of the spatial heterogeneity. So whether it is city size, this is the factor we are mostly interested in, or the socioeconomic variables, the road network shape, or natural variables. So here, the capital cities seem to stand out, but not only. We also see in red a lot of coastal cities, for example, so this needs more exploration. This is the relative excess travel time, so in percentage against the population. So we see a trend, but there are several outliers. We also computed other aggregate indices weighted by the population at the origin. So this is again taking the strong assumption that the entire population is doing the trip. So just for an example, the total time loss in a city of more or less 380,000 inhabitants is of 27,000 hours per day traveling during the morning peak, and something similar during the evening peak. And this can be seen as a productivity loss because of road congestion. Here we finally show the log-log graph of the excess travel time during the morning rush against the population. So a power law over a log-log graph gives a straight line, and we found that the best exponent for our power fit would be equal to 1.5. It corresponds to a superlinear scaling of total congestion with city size. So what does this mean? Actually, it challenges the claims of sustainability of big cities. Agglomeration in cities, unfortunately, does not only generate economies. Congestion is a major diseconomy associated with the concentration of people. So for largest cities, delays due to congestion actually dominate the time spent in traffic. And economical losses per capita due to the time lost in congestion increase with the size of the city, not even mentioning the corresponding strain on people's life. So this superlinear scaling was already shown on a set of American cities, but it was smaller, it was of 1.27. Okay, so the next steps of the research is to recompute these indices on rescaled cities to offer a solution to the modifiable area unit problem, applying a formula linking city area and population. Second since this paper is about aggregated measures and the effect of population size, adding a public transport counterpart seems highly necessary, because the agglomeration literature would make the case for higher possibilities to invest in public transport when cities grow bigger. So we will compute a multimodal access time with the same methodology as for automobile trips. We are also analyzing the effects of city size on mode choice. And finally, we will find a more robust scaling of radial profiles, like I've shown you just after the data, to see whether cities of different sizes can overlap and show the same behavior relating to travel times. Thank you for your time. And don't hesitate if you have recommendations regarding the indices or the interpretation.
Thanks very much for your presentation, Estelle. That was really good and really interesting as well. So again, I'll ask if anybody has any questions. You can type them in the text chat and I'll gather them up and present them to Estelle. So there's some questions coming in already. So again, thank you for the presentation. Do you think it is possible to use these methods, indexes, especially the congestion index, to predict urban sprawl in big cities?
Yes, I think this is highly related to urban sprawl, indeed. That was actually one of the objectives, to have a new measure of urban sprawl with this kind of radial methods. So definitely, yes.
Okay. And another question. So any impact of city policies, e.g. support for public transport or congestion management charges?
Yes, it's difficult to study each city individually because we have a high number of cities. So I tend to be very cautious about making policy recommendations, because here I really try to establish a general law at the European continent scale. But yeah, if we look more in depth into each individual city, yes, it could work.
Yeah, for me, 1,000 lost hours in travel time was depressing, even for a small city. So I guess what interventions, we think about what interventions we can make to improve this situation. And again, this research could be the start of that, or at least head people in the right direction of policies. So there's another question then. So again, very interesting, and thanking you. I have a few questions. Firstly, do you plan to integrate explicit spatial transportation into the Alonso spatial profiles theoretical framework? So do you want to tackle that one first?
I'm not sure what you mean by explicit spatial transportation.
Okay, we'll maybe get some clarity in that one and come back to it. So the second part of it then, I guess, is did you benchmark travel time from Google with, for example, results from simple transportation models, betweenness and user equilibrium?
No, I really took the brute, the raw data from Google. Yeah, not to have any additional bias after when we compare that with the total population of the city.
Great. So yeah, I guess I was wondering there in relation to that was, you said that a lot of the existing studies just use Euclidean distance rather than travel time. And do you have a sense for what kind of difference there would be in terms of the output of the work from using Euclidean versus using travel time? The take-home message from it, I guess.
Yeah, exactly. Yeah. And yeah, this can be applied very easily. Yeah, can be applied to a big range of cities and not only to one specific case.
Okay, so there's a third part of the question then. So you answered, for larger cities, transit is important. And may congestion be mitigated by more transit?
Yeah, that's why we are hoping. That's what we are hoping to discover by calculating the same data from Google on public transportation to see, yeah, how much it can play in this traffic.
Yes, I think it's getting down to convince people to use public transport is a key thing. So there's a clarification then on point 1. So the link is to distance to center radius. Would it be possible to integrate an explicit transportation network as you did empirically? So I guess, is it to use an actual transportation network and apply it into this model, maybe, is the question. I'm not clear on it either.
Okay. So it's a theoretical transport network, I guess.
I think so, yeah. Maybe have a look at the link after and
Yeah,
see what the paper there on that link afterwards. Okay, thank you for that. So are there any other questions? Oh, so there's one coming in. So can Google give historic real-time public transport estimates, both average journey times, but also reliability and variation in public journey times, public transport journey times?
So Google does not allow to have past traffic data. You can only estimate traffic in the future. But of course, it's based on past data, but the Google algorithm is more or less a black box, so it's difficult to understand exactly how they predict the travel time in the future. But no, you cannot have the data in the past.